Hello. Thank you. So yeah, I'm Jack Vanlightly. I'm a software engineer, mostly doing data engineering, distributed systems, event-based systems. And recently, in the last couple of years, I've been doing a lot of testing of distributed systems. So I've been working in messaging systems. That's kind of my thing, is messaging systems. And most recently, I'm working on RabbitMQ testing of the next RabbitMQ release, which is 3.8, which has two new distributed features. One is Quorum queues, which is a raft-based replicated queue, and also single active consumer, which is a consumer coordination feature, both of which are distributed and need to work across multiple nodes and survive broker failures and all kinds of edge cases. So people say distributed systems are hard, and that's true. It always comes down to the same problems, that they're hard to reason about and hard to test. Basically, we've got multiple processes and actors all interacting concurrently in a system. We have race conditions, failures. There is no now, so different servers can have different idea of what now is. There can be clock skew, so we can't rely our algorithms on timestamps. And there can be all kinds of unanticipated sequences of actions and events. So we have an explosion of possible interactions, and there's just no way we can always come up with a design and that is always correct in all the different possible sequences of actions that can happen. So we're going to look at Apache Kafka replication as like a case study for this talk. We're actually going to look at an old version of the protocol, which actually has a defect, which has since been fixed. And we're just going to learn about that, and then we'll use that as the basis for looking at our strategy. So with Kafka, we send messages to topics, and topics can have one or more partitions, and a partition is just basically a append-only replicated log, okay? And it's replicated because normally we'll have multiple copies of that log. So we'll have, in this case, a replication factor of 3, where we have a leader, which receives all messages. So producers and consumers always interact with the leader. And then followers get replicated the messages. And so the follower's job is just to be there in case the leader dies and they can take over, because we want high availability and we want data safety. So we're going to have a look about how the replication works. So we have here just a replication factor of 2. So we have a leader replica and we have a follower. So when the leader receives a message, it has its log end offset. That's the message that at the end of the log, the offset. So that's like the position in the log. So it has a log end offset of 1. And the follower is every 500 milliseconds sending a fetch request. It sends a fetch request, and that way it is able to get the latest messages. So it sends a fetch request, it gets a response, and it gets the latest message. In the next fetch request, it also is able to tell the leader what its log end offset is. And so the leader now knows that the follower has the first message. And now we can set the high watermark. And the high watermark is where we can kind of mark which messages are safe. They are committed, okay? When they get to this point, except for some caveats, Kafka kind of guarees that it won't lose those messages. So the high watermark is very important. It's basically saying, once the high watermark has reached this offset, all messages from this offset and down are safe. And so in the fetch response, it also replicates what the high watermark is. And because the followers need to know what the high watermark is, because they may become a leader in the future. More messages come in, so we have more messages received. The log end offset also is increased. Another fetch request is sent. A response is sent, and the latest messages are now on the follower. Another message comes in to the leader, and another fetch request is made. At this point, the high watermark increases in the leader because the follower said, I've got message 3. Give me anything new you've got. So the leader knows that up to message 3 is safe. And so it sends its response, and it carries on like this. And we get more messages in, and we get fetch requests and responses, and messages and the high watermark are replicated to the follower. So, what happens when a leader dies? So when a leader dies, a follower takes over. So in this situation, we have, if I go back one actually, so we have 4 messages on the leader. Follower A is fully caught up to the leader. Follower C is lagging a little bit, but only a tiny bit. And they're both considered in sync, which basically in Kafka terms means they've been fully caught up in the last 10 seconds. But then the leader dies. At this point, both A and C are candidates to become the new leader. What happens when A becomes the leader? So now, follower C sends its fetch requests to the new leader, and it sends a fetch request, and it gets the latest messages. It gets replicated the high watermark, which is now at 2, just like the leader. Another fetch request comes in. At this point, that fetch request includes the log end offset, which is 4. And so leader A now knows that 4 is safe and moves the high watermark up. And in its response, it's able to communicate to the follower that the high watermark is at message 4. New messages come in, more fetch requests, we advance. Leader B comes back. Okay, it's now a follower because we can only have one leader. So the first thing it does, and this is very important in the protocol, is it truncates its own log to the second message. It does that because right now it knows the second message is safe, and it cannot trust anything above it. So it just truncates, and then it sends a fetch request saying, hey, I've got 2, give me what you've got. It gets the latest messages, the high watermark is 5, and there we go, we've had a leader failover without message loss. Now, we can also have leader C win the election, because at the moment, the high watermark is actually 2. C doesn't know it's 2, but B, the leader, knows it's 2, and that is basically saying what's safe. And leader B dies, like before, and C becomes the leader. Okay? So follower A sends its fetch request to C, and C says, hey, wait a minute, I don't have 3 and 4, I've got 2. So it truncates, and now more messages come into the leader, the follower sends fetch requests, and we've got the same messages in both the leader and follower. B, oh yeah, and more fetch requests advance the high watermark. So now B comes back, and we've got a problem. It's got messages that don't exist anywhere else, and it has to eliminate those because otherwise it's going to have a different copy of the log, and this is something that Kafka guarantees it won't do. So what it does, as before, is when a node comes up, it truncates its log to a high watermark that it knows about, and then requests the latest messages. And so although we lost messages, this is actually a legal loss because the messages we lost were not safe, and Kafka will happily lose unsafe messages, and clients can choose to either care about that or not. Clients can say, only acknowledge when they're safe, or they can decide to just, hope. But we've got a situation, this is how it should work, okay? But there's actually a defect here, and this was a defect that existed up until a few years ago, and then they fixed it with a different mechanism. And it's all around the high watermark, which was supposed to protect us from having log divergence, where we have a leader and a follower with different copies of the log. Let's have a look what happens. So follower B is a little bit behind A, and it restarts. Yeah, maybe it crashed and got rebooted, or the administrator decided to reboot the machine. Anyway, when it restarts, it truncates its log to its high watermark. Then it sends a fetch request. Now, if the leader could respond and send those messages, we're okay. But if the leader now fails, we have a problem. Follower B gets promoted to leader. Follower A comes back. It says, give me, well, first thing it truncates its log to what it thinks is the high watermark, then sends a fetch request, and leader says, hey, no, the last message is 1, and now we've just lost a committed message. So the point of this is that it's quite a rare event that you would have a follower reboot, and then the leader fail or reboot just after that. But it can happen. It's one of these edge cases, and distributed systems are full of these edge cases. And so we need a strategy for how we can build distributed systems where we can avoid these protocol defects as far as we can. And that's what this talk is about. And we'll be using this Kafka as a case study. So we've got the testing pyramid. Okay, everyone's seen that. It's been around for a few years, where unit testing is fast and it's cheap, and so gives the best return on investment, followed by integration testing and UI testing. Then the automation revolution happened, and we've got more integration tests are now a possibility. You know, some people, for certain projects, they like more integration testing with new technologies like test containers, and containerization has revolutionized testing. And so, you know, some people now are suggesting the testing trophy. And I am now suggesting the testing cafetiere, which is something specifically for distributed systems, where at the base we have formal verification, and that is like a foundation we build on, and then we have the same unit and integration tests as you're used to, in whichever kind of flavor of that as you want. And at the top we have randomized systems tests. And these are tests that we start to work on once we've already got quite mature unit and integration tests. And you see from the handle, we've got some arrows, and it indicates that the randomized testing can actually feed our integration and unit tests. So let's start with formal verification. So one of the first proponents of formal verification in industry by practical engineers, not just in academia, was AWS. And they actually started using TLA+, which is a formal verification language, to verify S3, DynamoDB, and now tens of their services. And in their paper that they wrote, they said that human fallibility means that some of the more subtle and dangerous bugs turn out to be errors in design. And we've just seen a protocol defect that was purely a design. The code that Kafka wrote implemented the design, but the design was wrong. The code faithfully implements the intended design, but the design fails to correctly handle a particular rare scenario. We have found that testing the code is inadequate as a method to find subtle errors in design. That's not to say that testing, they don't do testing, they do a lot of testing, but they've found that they need something more to find some of the edge cases in their distributed systems, which they rely on massively. And you think what happens when S3 goes down, because so many other services depend on it, and so many clients depend on it. So what is formal verification? So we know that testing isn't always enough. It's necessary, but it's not sufficient. So Wikipedia says that formal verification is the act of proving or disproving the correctness of intended algorithms with respect to certain formal specification or property. And in this conference, there's a few talks on property testing, and this will be in a similar vein. Using formal methods of mathematics. At this point, engineers, most engineers, and myself included, before I started learning about TLA+, it's kind of scary, right? We're going to be using mathematics to verify our algorithms. And that kind of sounds like it's just for those super clever rock stars that are building Google's massive global infrastructure, not just an engineer like me. But Ron Pressler, who's a big name in TLA+ and formal verification, he says that TLA+ is a formal specification and verification language that helps engineers design, specify, reason about, and verify complex real-life algorithms and software or hardware systems. So no talk of maths there. It sounds pretty reasonable. It sounds quite interesting. And in the Amazon paper, the way that the initial teams that used TLA+ to verify S3 and DynamoDB, when they were trying to sell the use of TLA+ and its cousin PlusCal, which is a form of TLA+, the way they put it to their other teams is that it's just exhaustively testable pseudocode. Okay, so you don't need to you don't need to think about it as formal mathematics. You can just think of it as just another pseudocode. So that sounds pretty cool. So it's not all about correctness. It's also about designing. It's also helping you use abstract concepts and a more abstract language to have precision in your designs, okay? So in order to find subtle bugs in a system design, it is necessary to have a precise description of that design. In contrast, conventional design documents consist of prose, static diagrams, and perhaps pseudocode in an ad hoc and testable language. Such descriptions are far from precise. They are often ambiguous or omit critical aspects. If you go to the wiki for Apache Kafka, they've got an excellent wiki where they describe in prose all their protocols, and it's a really great way of learning how Kafka works, but it's not enough. So it's about verifying correctness. And Leslie Lamport, who made TLA+, the inventor of TLA+, and he said that correctness of the algorithm means that the program satisfies a desired property. And so the way that TLA+ can prove our correctness is through properties. So what is a property? So going back to Apache Kafka, well, one property is that committed messages are not lost. Once a message is committed, it will not be lost. Unless, of course, you lose every broker. But given you don't lose every broker, messages are not lost. Messages are stored in temporal order. Up to the high watermark of a given partition, each replica consists of the same messages in the same order. So that means we cannot have messages 1, 2, 3, and 5 on one, and then messages 2, 4, 6, and 7 on another, if they're both below the high watermark. And these are called safety properties. So a safety property is true in every reachable state. So it's something that's always true. So not losing messages is always true. We cannot have a single situation, except total loss of the cluster, where we can lose messages. And this is known as an invariant. Other types of properties: if a message is sent to the leader replica, it must eventually be replicated to all followers as long as the leader does not die. If a leader dies, there are followers, then eventually a follower will be elected leader. So these are liveness properties. These don't say, these say when something must happen, or that something must eventually happen. The fact that we don't lose messages must always be true. But when a leader dies, all liveness properties say is that eventually a follower must be elected leader. So a TLA+ specification describes the behavior of the system. So we have, fetch requests, fetch responses, we can start and stop nodes, and it has the properties, the safety properties and liveness properties. Then what makes it actually relevant to us is there is a model checker. We can actually run our specifications, and we can actually get results. So it's not just some mathematical formula that you have to parse yourself. You can actually execute it with the model checker. And the model checker will exhaustively test every single possible sequence of action that is in your specification. So it's kind of like a testing framework for designs. So going a bit more into what TLA+ is, so it models time. It's not a continuous time. Everything is discrete steps. A step happens, which models the state, and then another step happens, which models the state. So we have our initial state, and then we have a step, and another step, and another step, and another step, all while modifying the state. And we go from one state to another state. And each step can consist of one or more actions. So what kind of actions do we have in our system? Well, we can start a node. We can shut down a node. We can become the partition leader. We can receive a message. A node can become a follower. A follower can send a fetch request, and a leader can send a fetch response. So what states are in our system? So one state would be that we have a single node without a role with no messages. Another state would be that we have a single node that's leader with no messages. Another state is that we have a leader with one message and the high watermark is 1. And another state is that we have 2 messages, and so on. And we can quickly see that the number of our states can increase, because every time we add a message, we're actually creating a new state. And so our state space can explode exponentially as we receive more messages and there are more interactions. And so this state explosion is something that if you get into TLA+, you're constantly fighting against it. Because if you want to use the model checker, unless you have a controllable amount of states, it might never finish. You could run it for thousands of years if your model is too big. So we tend to see quite small models. And usually, we can actually find defects in a protocol with just 1 or 2 messages sent. And in fact, we'll see how we can find the defect in this protocol just by sending 2 messages. So this is a traditional state machine. This is a circuit breaker, which you may be aware of when you're doing software development. And it has 3 states. But with TLA+, this is not, we don't have simple states like this. A state in TLA+ is all of the variables in your system. So, for example, we start a node, we have one node without a role. That's the first state. And then another state after it becomes leader, and another state after it receives a message, and it receives another message. It's got log-end offset of 2. Then we start another node, and we have a second node without any messages. It becomes a follower. That's another state. It sends a fetch request. So now we have a pending fetch request at the leader. That's another state. And so as we do more actions, we can uncover more states. So how do we represent state in TLA+? It's just through variables, just like any good pseudocode. And how do we represent steps? And these are through formula. Okay, we have everything is a formula in TLA+. So we have an initial state formula, and this is where we basically set the values of our variables in the beginning. And then we have a next state formula, and the next state formula is executed again and again and again, reaching every single possible state. Okay, so here's an example. Each action that we've got in our system can either be enabled or disabled. So in the initial state, we have nothing. We have no nodes. Nothing is started. So we can't receive a message or send a fetch request. All these actions are disabled. All we can do is start a node. So we start a node, and now we have more actions which are enabled, which could be executed by the model checker. And in fact, the model checker will execute all of these. Imagine an infinite number of parallel universes where each time a different thing happened, and that's what the model checker does. It just exhaustively explores the entire state space. In this case, we start a new node, and we've still got the same actions that are enabled. So this time the model checker chooses to become leader, because we've got 2 nodes without a role. And now, because we've got a leader, we have more actions which are enabled. So we can receive messages now. Also, now that we have a leader, the other node can become a follower. So the model checker chooses to receive a message. And now we have the same actions enabled again. And the model checker chooses to become, for the second node, to become a follower, and so on. So let's have a look at some TLA+. So we have constants, and this is something which you can set from the actual, from the toolbox, and the toolbox is the sort of TLC model checker where we run our specifications. And so in this case, I'm just going to have 2 nodes, N1 and N2. So we've got variables. This is our node data. This is just an array. And each item contains information about the node. It contains its ID, its log, the high watermark, the log end offset. We have the ID of the current leader. We have the confirmed log end offset of each replica. So this is something that the leader maintains, so it knows what's the latest log end offset of each node. We have the pending requests. This is also something the leader maintains. This is all the pending fetch requests that it has to send responses for. And then some stuff that's just used by the specification. The current value is simply a counter, because for our properties, we have that we cannot lose a message, but other properties are that it's in temporal order. And so to be able to test order later on, we use a monotonic counter, and we increase the counter by 1 for each message. And each message simply stores a number. And later on, we can check that the numbers are in the right order. And we have committed messages, which is a set, which we basically, every time that the receive message action is executed, we append it to this set. And this does not exist in the protocol. This is so the specification can detect message loss, because we'll see that we can have a property where we check the messages in the leader node and make sure that every single message in our committed set is there. So I said we have the initial state formula and the next state formula. So the initial state formula is where we essentially just assign values to our variables. And this is how so dash basically means that there is no leader. Node data is for every n in uppercase N, so that's N1 and N2. We set its ID to N, we set its role to offline, its high watermark to 0, the log end offset to 0, and it has an empty log. Pending requests for every node is empty. The confirmed LEO is also 0, and the committed messages are empty. So this is, and our counter we set at 1. So this is how everything starts. Everything starts empty. We have nothing. So now we define our actions. So we have our next state formula, okay? So here we've got our slashes, which can mean and or. I'm not going to go into too much detail about this and there exists, because we only have so much time. But I think you should be able to get the gist of it just from these slides. So offline nodes is another formula. Okay, it's a definition which will represent all the offline nodes, which we'll see in a minute. And it basically says that we could start a node. Okay, if an offline node exists, it could be started. Then live nodes. A live node could be shut down, or it could become leader, or it could become a follower, or it could send a fetch request, or it could send a fetch response, or we could receive a message. All of these are sub-formulae, okay, and we're going to have a look at what these are. Just like in programming, you've got functions. You can decompose your big formula into lots of tiny little sub-formulas, just like you do in programming. So our live nodes formula basically says for every node in our constant, which is all the Kafka nodes, its role cannot be offline. And it basically creates a set filtering that it cannot be offline. Okay, so and that's basically a formula that represents all the live nodes. Okay, so we have this set and filter syntax. In Python, you would write some kind of loop. And offline nodes is just where they're offline. What about start node? Well, I said that actions can be enabled or disabled. So here, our enabling conditions are that it has to be offline. Okay? So if this first formula is not true, then it cannot be executed in the model checker, right? And we also say what the next state will be. So we cannot mutate the current state. Okay? We have a state, and then we have the next state. And all we can do is we can say what something will be in the next state. And we use the little apostrophe there. And so the node data in the next state will be the same as the node data in this state, except that for this specific node, its role will be none. It's a very strange syntax, but you get used to it. Also, because when we start a node, it has to truncate the log. Okay, so what we do is we set the log end offset to the same as the high watermark, and we truncate the log to the high watermark. Okay, and so here I'm just creating a new set based on the current set, but where the offset is equal to or lower than the high watermark, and that basically truncates it. We can shut down a node, so it has the enabling condition. I say cardinality. This is a way of doing a count of a set. Okay? In my specification, I'm not interested in modeling shutting down everything. Okay? I just want to model that at least I have one broker. So I say it's only enabled if there's more than one, and that this particular one cannot be offline, because that would make no sense. And in the next state, it will be the same as in the current state, except it will be offline. And we'll also need to modify the leader node variable. So if we are the leader, then if n is the leader, then the node leader in the next state will be dash, signifying that there is no leader. Else it remains unchanged. And anything else, we can use the unchanged keyword, because every time we execute some action, we cannot just say what it changes. We have to say what it doesn't change. Because when we go from one state to another, it includes everything. So we have to include everything. So even if we have a huge amount of variables and we only change one thing, we have to explicitly say that everything else remains unchanged. What about for receiving a message? Well, the enabling condition, first of all, we have to say that there has to be a leader. Okay? If the variable is dash, then that means there's no leader. In the next state, we can use let here to simplify our formula, and we'll just be using message offset further down in the formula, and we'll just say that the message offset of the new message will be the current log end offset of the leader plus 1. So, and here we say that the node data, so this is the data of all our nodes, will be the same as the current one, except that of the leader, its log will be the union of itself plus a new message, and the new message has an offset and a value. Don't worry, you don't need to understand everything here. It's just to get a gist of what tla-plus is. And we set the LEO of the leader to the message offset. We increase the counter, and we update the confirmed LEO to the message offset for that leader. And everything else remains unchanged. So that's what it should do. Okay, that's like the behavior of the system. Not all of the actions, but some of the more simpler ones. And now we're going to look at how we can set the safety properties, our invariants. Okay. So this is our another formula. Okay, and the model checker can always check to see if this formula is true. If it is false, then the model checker will stop. So one thing is it's valid for there to be no leader. Okay, we don't want it just to fail just because there's no leader. So if there's no leader, then we can't check to see if there's been message loss, because we need to check once there is a leader again. But if there is a leader, then that /a means for all. It's like saying for each message that we have in our committed messages, that message must be in the log values of the node leader, which is another sub-formula, which is basically, again, this is a different syntax where we basically can create a projection, and we're basically doing a select val from the log of the leader. And when I run the model checker, it finds this sequence of actions violates that invariant. So it's just like earlier. We start node 1, and then we start node 2. Node 1 becomes leader, node 2 becomes follower, and the leader receives a message. The follower sends a fetch request. It gets a fetch response. So it's got the first message, but its high watermark is still 0. It sends a fetch request, and then another message comes in to the leader. The leader sends a fetch response, and at this point, the follower has 2 messages, and its high watermark is 1. It then shuts down and starts up, and this is where we restarted it. And so at this point, it truncates its log to its high watermark, which is 1, and then the leader fails straight afterwards. And at that point, node 2 becomes leader, and it's lost a message. It's a slightly different order because there are actually tens or hundreds of specific interactions that can lead to the same thing. They're more or less the same. But there are actually, I think, probably hundreds of specific interactions that will lead to that message loss scenario. So it is weird and wonderful. At first, it will break your head. It will break your brain. You will go through periods of triumph and desolation as you struggle to use it. But, you know, think about that SQL. If you remember being a junior developer and you first see SQL, or imagine looking now at a very complex SQL query and you'd never seen SQL in your life. You know, it would just be nonsense. It's just a matter of learning another paradigm. So, yeah, it took me 2 to 3 weeks to create my first real specification, and I actually found a real bug in my own protocol. And it wasn't actually the interactions of the nodes themselves. It took the interaction of an admin to do something as well. And if an admin did something in a particular order, it would actually cause the system to become inconsistent. So that's the base. Formal verification. Okay, very much a quick talk on TLA+. So what about randomized system testing? Let's see what that's all about. And so it's basically a form of property-based testing, okay, where we check that certain properties or invariants hold while executing the program with different inputs. And that sounds remarkably similar to what we just covered in TLA+, which is where we model a system, we execute it with different inputs, and properties, invariants, when violated, can tell us when it's got a defect. So, you know, 2 sides of the same coin. So, what do we do in randomized system testing? So, we just decide on some properties, invariants that we want to make sure are true no matter what we do. All the while, we take a set of actions. So what actions can we do? Well, we could start a node, stop a node, send a message, read a message, rewind and offset, add a partition. There's just an endless list of things you could do with Kafka. Now, the difference here is that with TLA+, we're modeling the entire system. So you will not see send fetch request in this list, because that's what Kafka does itself. We're operating from the outside externally and just doing external actions. And you can be really nasty with the intervals. You might think, oh, well, you know, such and such action probably will only happen once an hour or every week. Well, we can do it, make it happen every 5 seconds. And sure, the thing will probably fail, but how does it fail? We want to make sure it fails in a deterministic way. And, you know, so you can be as nasty as you want with your intervals. We can add more randomness if we want. You would probably want to control how much randomness you do, but we can inject failure. This is quite a common one. And we can also test the configurations and features, because one thing that can be difficult, as we saw in the, not sure if anyone saw the Java testing talk, is that the number of different configurations can make things very difficult to test, the number of configurations that you need to test. So what kind of failures can we inject? So we can kill TCP connections, we can add latency, we can introduce packet loss, we can kill nodes, we can destroy data, we can corrupt data, which is really nasty, and a lot of systems cannot cope with that. We can do things like network partitions, we can do clock skew, and so different servers have a different idea of what the time is. And we can use different configurations. So this is just a small number of the different configurations you can get with Kafka. We could set a different replication factor. We could use log compaction, yes or no. We could use different producer acknowledgement modes. We can use the deduplication feature or not. We can change batch sizing on the client. You name it. There's something for everything. And that's one of the more difficult things, is choosing how to tackle that problem, because many of the problems that I found in my RabbitMQ testing is the combination of features. The last build which failed, which is an alpha after beta 3, failed because of the combination of 3 features along with a failure. So we're doing all of that, and we're recording everything, because later we're going to need to analyze exactly what happened if something did fail. So we want to know what the root cause was, which can be difficult, because let's just say we detected message loss. So now we have to go through the logs and decide what caused that. It's not like a nice little unit test where, oh yeah, I know it's that class. It, you know, literally could be anything. And we want to make them reproducible. So we can then add these failures to our unit and integration tests. Hence, on the handle of the cafetiere, these can feed our unit and integration tests. Because once we've discovered it, we can then make sure it doesn't come back. So unit tests are fast. Integration tests are a bit slower. And randomized system tests are maybe akin to star formation. They can be very slow. And this is one of the downsides, because they can be slow to run, simply because you want to add as much entropy as possible. You want to explore as many of these different random sequences of events and failures as you can. But also it can be very slow to analyze, because you've got a failure, and now you need to diagnose. So it's all about your logging, and looking through code. And you might want to parallelize things. So I tend to not do randomization too much of configurations. I might choose specific configurations and then randomize everything else. But you can easily run these things nightly. You just set it up in Jenkins, make each test agent send everything to S3 or wherever you want, and you can get an email. So with Quorum Q testing, this is one of my main things I've been involved in the last few months. And one simple test, which I've got multiple different tests for RabbitMQ, but the simplest one is where I have a single producer. And all it does is it sends messages with a monotonically increasing integer. So 1, 2, 3, 4, 5, and that's all it does. If it loses its connection, it reconnects. If the broker dies, it connects to another broker. And it just keeps sending these messages. Then I have a single consumer, and all it wants to do is consume those messages. And if the connection dies or the broker dies, it just reconnects. All the while, it's analyzing both the order, and we're analyzing which messages have been received. Because later we'll be tallying. The producer says, hey, I got 400,000 positive acknowledgements that my messages were saved. And the consumer says, well, I only got 399,000. And we can actually discover message loss. And then at random intervals, we just can start and stop nodes, RabbitMQ nodes. We can start and stop consumers, which is a common thing to do. We can get a bit nastier, and we can kill consumers, make them crash, and restart them. And we can inject failures. We can mess with network, kill brokers, that kind of thing. And we can make it as long as we want. And then I have a 5-minute grace period at the end where we allow the consumer to catch up, because sometimes the producer can get far ahead due to connections, killed connections and things, and then we let the consumer catch up, and at the end we compare what they've got. And we can just check for message loss, and we can check message ordering. And in every single beta so far, and every single alpha, I've managed to find a violation of one or both of these invariants. Because it is really hard building these systems to tolerate failure. The number of edge cases is quite large. So this is just a little animation that I did, because I learned how to do PowerPoint animations, as you've probably seen. So I thought I would do one of this test. So I use something called Blockade, which uses Docker to host. I use it for Kafka and RabbitMQ testing, and also Apache Pulsar. And it can just do all the chaos I need. I also use Proxy, which is a proxy where I can introduce latency, I can kill connections, I can reorder packets, all kinds of stuff. And then all the while this is happening, I'm collecting logs, and at the end we just see if those invariants have failed. And the great thing about using a monotonically increasingly integer for the messages is that when we can see exactly which messages were lost, and so we can see in time where that message loss happened. It's not just 10 random messages. We know the exact messages that were lost, and then we can analyze exactly what happened around that time. And then we can, quite often, because I run these for like 8 hours, we'll have the same error happen 3 or 4 times, and you can see the same sequence of events happened each time. And then the RabbitMQ team find the problem and add it to their regression tests. So not everyone likes coffee. I have one friend who doesn't like coffee. Crazy, I know. So there's the testing hamburger as well, just in case. So where can you learn about TLA+? My favorite is the video series. And it's just great. It's really quirky with Leslie Lamport. And it starts off, well, it's kind of hard all the way through, but it gets progressively harder. And you'll probably need to rewatch videos a few times towards the end, especially as it gets into liveness, because the safety properties are the easier bit, but they're also the most useful, and the liveness properties get a bit more complex. Then you have the Specifying Systems book by Leslie Lamport, which again is very in-depth. If you really want to get into it, that's a great way. Hillel Wayne is quite big in this space. He concentrates mostly on Pluscal, which I have not shown today, as I do not know how to use it yet. But Pluscal is like a pseudocode. It looks like code. It's not as powerful. There's many things it can't do. So I kind of went for TLA+, which is more powerful. You got the subreddit and the Google group. The Google group, it doesn't matter what question you ask. Half the questions are complete newbie questions, and everyone is super nice. Leslie Lamport himself is often in there answering questions. So get involved. Regarding random testing, Carl Kinsbury started it all back in 2013 with his Jepsen analyses, where he kind of broke various distributed systems. It's what originally got me into distributed systems, and his analyses are great for understanding how they work, because he breaks them and shows you exactly why, how kind of distributed systems need to be designed. It's a really great source. ToxiProxy is great. It's just got a REST API. You can create proxies. You can integrate these ToxiProxy into your integration tests as well very easily. And you can do simple things like cutting connections, or you can add latency. You can do all sorts of things with network. Blockade is something that I use quite a lot for my RabbitMQ testing. And it just allows me to host RabbitMQ in Docker, which is, containerization makes these tests a lot easier. And then trivially lets me sort of start and stop stuff, mess with the network, all sorts of things like that. If you want to have a look at any of my code around RabbitMQ, it's all on one of my repositories. And another great source of learning about testing distributed systems, which I have to say is a massive area, okay? It's just huge. There's so many different, and it's a very active area of research. So Andre has a GitHub page, and I highly recommend going through it. It would take you a long time to read it all, because there's a lot there. So there we go, the testing cafetiere or the testing hamburger, whichever you prefer. And that's it. Thank you.
Thank you. We have time for a few questions.
Thanks for your presentation. I wanted to ask if you have any idea of how to automate this analysis after your test, because, yeah.
The analysis, yeah, that's the bit that you can't really automate. What you can do is you can make sure that all the information is in one package, if you know what I mean.
Okay, so is there, you mean something like log combination, like using ELK or something like that, right?
Using what, sorry?
ELK?
Yeah, you could use that. I mean, yeah, so I often use like a time series database for things like metrics, and then in my test report, I can actually create a link to where that, where those graphs are. So rather than having to do a search, you can just in the log click on links and just open up on your dashboard. So you could easily, if you know the timestamps and things, you can easily just create links just so that that's the downside of the random testing, is the time of analysis afterwards. But if you arrive the next morning and you've got an email with a bunch of links and any failures, but also the point of this is that these tests are kind of like automated exploratory tests. Okay, so if you've got mature integration and unit tests, then you shouldn't be seeing loads of failures all the time. You probably get a period of instability when you add new features and things, but then you should see it settle down. So, because you can always reproduce the failures in your example-based tests afterwards. So it's really something you start once you've also already got a mature complete automated test set up.
Okay, can I have another question? Yeah, something similar. For example, I have 7 developers, and I'm the only one tester in the team, and I'm doing manual and automated tests. So, I mean, there is really a lack of time to get to this kind of tests.
Yeah.
I mean, flaky tests, some load stress, or something like that.
It really depends on what you're building. I mean, if you're Amazon and you're building a system that everyone depends on, then you're going to invest. If you're building a safety critical system, you're going to invest. But if it's a business system that's internal, then you might, depends,
yeah, I mean,
right?
it's an internal system, but it's like critical because you cannot have, for example, data loss, and that's distributed. So microservices is like in. So my question is that how can I maybe tell others that that's important and I should have time for this?
Well, one great way is actually going into your bug system or if there's been any outages or any problems with customers because of data loss or something, that you can show that this is a problem that exists right now, I guess. Other than that...
But that's kind of like post-active? Like you already had some incident and then you tell that, yeah, see that to that sense.
Yeah, I mean, there's also, I mean, you could do a cost calculation, right? Okay. What managers would like is, this is the projected loss to our company in terms of reputation, the actual lost client, potential litigation, and present risks, and you just present risk analysis and the potential costs.
Yeah.
I mean, that's, I guess, what you could do.
But still, you have to have time for risk analysis as well.
Well, that's when you have to say you need more people, I guess.
Okay, but thank you.
Okay.
Thank you.
All right, and last question.
Thank you for your presentation, and I have a question. Do you have some examples of TLA-plus in open source projects so I can see in the lab?
Yeah, you can go on to my Vanlightly, actually no, it's on something called Rebalancer. Rebalancer is a client library, which what I needed it for was with RabbitMQ. So with RabbitMQ, I wanted to be able to partition a queue, and they've got a partitioned exchange, and you can create multiple queues, and you can partition your messages across the queues. The problem is that you have no consumer coordination. In Kafka, you have multiple partitions as a logical topic, and then multiple consumers are just automatically balanced and assigned the partitions, and we don't have that in RabbitMQ. So I developed a distributed resource allocation library called Rebalancer, and it would work in theory with any resource. It could be a file, an S3 document, RabbitMQ queues, SQS queues, whatever you want, and it just uses Zookeeper as the coordination backend, and you can have as many nodes or clients as you want, hundreds, and they will coordinate between themselves to agree on who gets which queue, and then every time a client comes and goes, they rebalance. If I add a queue, they rebalance, and so it's this very dynamic coordination. And then I have a TLA spec there that proves. I also have a blog post about it, which describes the defect that spec discovered. I can, send you the link, but it's called Rebalancer. You probably find it on my GitHub.
Thank you.